All right, so we're going to learn more on triple integrals in cylindrical coordinates, a very useful trick to deal with integrals with regions that have some symmetry along some axis. So last time we introduced the cylindrical coordinates. These are the equations to transform coordinates to cylindrical. Remember that the way it works is that we take the x and y, so if we have a point in 3D, we look at the projection, and then in the projection, we look at the radius and the angle from the x-axis, and then the z-coordinate is a z-coordinate. So all that is changing here is that we're changing the x and y are being changed to polar coordinates, and then in total is what we call cylindrical coordinates. So let's do some triple integral to see how useful this is, because such an integral, as you can see, it's going to get really complicated real soon as the first part is easy because the function inside does not depend with respect to z. So when I integrate x squared plus y squared, I just get quantity x squared plus y squared times z and then go from there. But in the next one, there's going to be a square roots, and it's just going to get more and more complicated. So we're going to interpret this region to try to figure out if there is a symmetry that we can exploit to do cylindrical coordinates. The fact that there is x squared plus y squared floating around, it already is a good sign that there is hope because of this type of equation that I can transform that into just r squared, and that would simplify things quite a bit. So what is happening here is, let's see first what's happening in the x and y axis is that I'm going, let me redo that axis. I'm going in x, I'm going from -2 to 2, and then integrating up to the square root of 4 minus x squared. What graph is that? What's the square root of 4 minus x squared is the graph of what function? I think I heard it. It's a semicircle, okay? So if you just set up y equals the square root of 4 minus x squared and square both sides, then you get y squared is 4 minus x squared, which is x squared plus y squared equals 4. So it's a circle of radius 2. So I'm going in y, I'm moving all the way from the top of the circle to the bottom of the circle. So the y is running all along there. So the base of this region is, everything is above a circle of radius 2. And then what's happening, the z coordinates, in z we have, I'm going to go from 2, that's a plane, so it's going to cut it off at 2. So let's now draw this region right like so. Z equals 2 is, as I said, a plane that is going to cut off my figure at the top. And then we have z equals the square root of x squared plus y squared. And what graph is that? I have, for example, if you take cross sections for y equals 0, what do I get? I get the square root of x squared, so I get the square root of x, or the square root of x squared, which is the absolute value of x. So the cross sections, when y is 0, look like y is 0, so look like this, 2 straight lines. And when x is 0, I also get 2 straight lines like this. And when I cut off at z equals 2, I get the circle of radius 2. I've never heard that sound. That was so neat. Okay, so when you cut off at z equals 2, what do I get? If this is 2, I get x squared plus y squared equals 4. So the cut is like this, and this looks just like a cone. Okay, so it is a cone. So I'm above the cone and below the z equals 2 plane. All right, so now I know how to describe this region, hopefully, in cylindrical coordinates. Let's see what are the bounds. So in cylindrical, I'm going to have, first of all, an angle. What are the possible angles of those points? You can look at the angles are actually determined in the xy plane. So if I take a point here, what are the possible angles? Well, the points can be anywhere in the circle, so I get all the possible angles. Okay? So the angles are between 0 and 2 pi. What about the radius? The 0 to 2, again, that is determined at the level of the xy plane, and the points can be anywhere from 0 radius all the way to radius 2, and it doesn't depend on the angle. I can go in any angle, I can go from 0 to 2. So there is no dependency on the angle. This is from 0 to 2. And now the z coordinate, let me write first the lower bound. It's saying that it has to go, the z coordinate is right here. The bounds for the z coordinate doesn't change. It's going from, well, it's going to change a little bit because I need to transform that expression now into the cylindrical coordinates. But I know that x squared plus y squared is r squared, so that tells me that z equals r. Okay? So it goes from r all the way to 2. So those are the bounds that describe the region in cylindrical coordinates. Any questions about how I'm finding those bounds? Yes?
Why is C's lower bound r?
The lower bound is really the square root of x squared plus y squared. But when you're doing these changes of variables to cylindrical, you change the x and y to cylindrical, and now I don't want any more x and y's. Everything has to be r and thetas. So I want to change this expression in terms of r and theta. So either you substitute x is r cosine theta, y is r sine theta, but we know that x squared plus y squared is r squared. So if I take the square root of this, I get that z equals r. Okay? So the z coordinate goes between r and 2. Great. So now I can express this new integral in cylindrical. So this is actually, we go from 0 to 2 pi in theta. We go from 0 to 2 in r. The z one goes from r up to 2. And now also, the inside is also r squared. X squared plus y squared. The function itself has to be transformed to r and thetas in z's. There could be a z in there, but there's no z. So x squared plus y squared is r squared. And remember that if I'm changing coordinates to cylindrical, I have to put in my conversion factor to this new set of coordinates. And the conversion factor is an extra r. And this is dz, then dr, and then d theta. Okay? And now I can integrate. This is 0 to 2 pi, 0 to 2. This is r cubed. There is no z there, so this is r cubed divided by 3. No. I'm integrating first with respect to z, so this is just r cubed. Z between 2 on r, dr, d theta, which is the integral of r cubed 2 minus r, dr, d theta. Okay? If I simplify this. This is 2r cubed minus r to the 4. And I can integrate that with respect to r now. That depends on r. That will be r to the 4 minus r to the 5 divided by 5. R to the 4 divided by, so there's a 2 and 4, like that. The integral of 2r cubed is 2r to the 4 divided by 4. And the integral of r to the 4 is r to the 5 divided by 5 between 0 and 2 d theta. And that I get, the inside becomes 16 over 10 d theta. And then this is 16 over 10 times the integral of theta between 0 and 2 pi, which is going to be 16 divided by 10 times 2 pi, which is 16 divided by 5 pi. Okay. The r to the 5th, I simplified all of this. I did it beforehand. And when you substitute that 2 in here, you get 16 over 10. Okay? Any questions about this in particular, the setup as a cylindrical? And you can see how much easier it is in cylindrical than it is in Cartesian. Nobody wants to do that. Okay? All right. Let's do another one. This one came up when we were looking at integrals in Cartesian coordinates of type 1, type 2, type 3. This one can be interpreted in several ways in terms of type integrals. For example, I could try to interpret it as in the y coordinate. Let's try to interpret this in Cartesian coordinates. So the y coordinate goes from 0 to 4. Okay. The x coordinate goes from the square root of y to minus the square root of y. And then the z coordinate goes between two functions of x and y. So I can, in fact, compute this integral. I could compute it as y goes from 0 to 4. X goes from minus the square root of y to the square root of y. The z is going from minus the square root of y minus x squared to the square root of y minus x squared. And then I have to integrate this function, the z dx dy. Okay? And again, this just looks like I'm never going to be able to pass this class if I have to do that in an exam. But we can transform it to cylindrical coordinates and hope that this is going to be better. However, you see that now the real symmetry of this object is along the y-axis. So I'm going to use cylindrical coordinates, but I'm going to convert to polar coordinates the x and z values, and then let y run as it's running now. Okay? So let's see how that works. So I'm going to, first of all, see what is happening in the xz plane. That's going to be my base. In the xz plane, when I just put y equals 4, I can see what the cross-section is at the top, like this cross-section right here. When y is 4, I get 4 is x squared plus z squared. So the projection down to the xz plane, or the projection to the left to the xz plane in this case, is again a circle of radius 2, like that. And then the function that I'm looking at goes from, for y equals 4, I have a plane that is going to cut off my this graph, which is a paraboloid in that direction. Okay? In this cross section, this circle is the circle that I drew over there, which is the projection in here that this is setting up above. So this graph is y equals x squared plus z squared. This graph is y equals 4. So now I have all my ingredients because I have points up to here in the x and z plane. So I'm going to convert this to cylindrical coordinates with respect to the y-axis. Okay? So this is going to be the radius, or the angle. You can see that the angle goes all around. The base is really a circle, an entire circle of radius 2. So the angle, it's again going up to 2 pi. We will see later an example where we are only working to the right of some plane, so then the angle might be 0 to pi, or if it's only in one of the octants, then it might be 0 to pi over 2. So these can change. The radius is again going from 0 to 2. There's no change. If that base was something more exotic, we saw, for example, a 4-leaf clover at some point. We were computing the area of one of the petals of a 4-leaf rose, they called it. That could be the base, and then build something on top of that. It could be something like this. But in any case, here, the radius is also just going from 0 to 2. And the y-coordinate is going from x squared plus z squared up to 4. And we won because these are just do not depend on y. And this y only depends on x and z. We didn't win quite yet because what is this? I want to convert it to r and thetas. What's x squared plus z squared in this case? It's also r squared, because now when I mean cylindrical coordinates with respect to the y-axis, what we're doing is that x is r cosine theta, z is r sine theta, x squared plus z squared is now r squared, because I've changed where the polar coordinates are to benefit from the symmetry of that object. So the y really is going from r squared up to 4. How did I get these bounds? So the question is, how did I get these bounds? I'm looking at trying to express this integral as a Cartesian, and I was running in y from here to here. Let me see another color that is more visible. So y is going from 0 to 4, and then x, for any given value of y, x is going from here to here. If you turn this around, this is x is plus or minus the square root of y. So this function here is x is minus the square root of y, and this function here is x is the square root of y.
Well, why doesn't it look the same for Z then?
Why doesn't it look the same for z?
Like the Z bound?
The z bounds depend on this other function. So the z for any given x and y, the z is given by this other function. This is saying that z squared is y minus x squared. So the z goes from plus or minus the square root of y minus x squared. So it is between those two functions of x and y. So now we have something like x and y, and two functions of x and y that are bounding my object. Great. So now I have those bounds. and I can set up my integral. Oops, I'm running out of space. So let me set it up here. The integral is going to go from 0 to 2 pi. The r is going from 0 to 2. The y is going from r squared to 4. The function itself is x squared plus z squared, which is r. R times the conversion factor, it's still r. And now, what are we integrating? Remember that these are the bounds for y. So the first thing we're doing is integrating with respect to y, then r, then theta. And that's a pretty simple integral to do because this is just the integral of r squared with respect to y. That will be r squared y, evaluate at 4 minus r squared. So that will be the integral of r squared, 4 minus r squared with respect to r. That's just a polynomial. Yada, yada, yada. And you get 128 divided by 15 pi. Okay, there's a little bit of work in there, but that's what you get. All right, let's keep going. Oh, yeah.
How do you know y came first?
Oh, y is actually, if you mean first, the one inside in the very, I think that is the last one. So I think of the integration as when you think of an integral like this, I think of y first runs from 0 to 4 because that y is the one that is not depending on anything. Y runs from 0 to 4. Then the x is running from minus the square root of y to the square root of y. And then the z values are going from a function to a function. So I do think about it as the first one is the outermost. But I think your question is, so how did I know that y was going to be in there? It's because I am interpreting the entire object as having a symmetry, rotational symmetry about the y-axis. So that is the one that I'm going to do last because you should like tilt your head 90 degrees to look at that object. And now if you look at that object like this, then you see the plane, and that whole object is sitting above the xz plane. So I'm putting a projection on the xz plane, see what's sitting on it, which was a circle, and then going in bound functions of x and z from a function x squared plus y squared plus z squared all the way to y equals 4. That's a good question. So is there a way to tell where the symmetries are without a sketch? In this case, they are telling me that the surface is bounded between two functions of y, right? And if I see that, I can already think like, okay, I would like to integrate y last because the y is going to be between two different functions of x and z. And is there a symmetry in that way? The symmetries are going to appear if the functions and the surfaces that we're integrating with respect to, they have those symmetries, which is that, for example, x squared plus z squared appears and nothing else, that's going to have a symmetry with respect to the y-axis. If it was before we had x squared plus y squared, though it's a circle in the xy plane, so we know that it's going to have a symmetry about the z-axis. If you see y squared plus z squared, that is a circle in the yz plane of radius 1, so that has a symmetry about the x-axis. So just by looking at the functions themselves, you can try to figure out what is going to be the best strategy of integration and what kind of change of variables may be the best one for me. Since we know that if I know that x squared plus z squared is r squared, that's the best case scenario because of I'm going to be integrating a square root of, then look for that, try to set that to be r squared, and that would lead you to think, okay, then x has to be r cosine theta, and z has to be r sine theta, so I'm doing a change of variables is cylindrical with respect to the y-axis. Very good. Okay, let's do one more. Find the volume of the solid bounded by the cylinder, x squared plus y squared equals 1. That is a cylinder because it doesn't describe what the z value is, so it's sitting all above that circle of radius 1. To the right of the xz plane, below the, okay, so lots of instructions. Let's see what this is. First of all, what is this cylinder? If I draw the circle of radius 1 here, then it's going to be the circle of radius 1 at every height. So let's put it like this. And let's set here 4, because I also have z equals 4, which cuts the cylinder at that height. Okay, so this over here is x squared plus y squared equals 1. That's the cylinder. Z equals 4 is a plane. So I already have a top region there. And then to the right of the xz plane, that cuts my object like this, like so. Okay, so I only get this part of the cylinder now. Okay. And it has to be above z equals 1 minus x squared minus y squared. What graph is that? The last one. Watch out for the squares here, so it's not a plane. If it was z equals 1 minus x minus y, it would be a plane. But because of the squares, it has to be some, has to have some curvature to it. It is not a sphere. It would be a sphere if there was a z squared in there. Yes? It is a paraboloid. X squared plus y squared is a paraboloid that opens up. Negative x squared minus y squared is a paraboloid that opens down. And then if you raise it by 1, then you get 1 minus x squared minus y squared. So that's a paraboloid that starts at z equals 1 and then comes down. So at z equals 1, there is a paraboloid like this. And we're looking for the region that is, let me try to draw it again like this, but it's hollow. Inside looks like this. I don't know how to draw it better than this. So inside is missing a little bit of the cutoff of the paraboloid. All right. So what the heck are we going to do with this? We are going to just use cylindrical coordinates because it looks like a cylinder to begin with, and it does have symmetries above the about the z-axis. So what are the cylindrical coordinates here? I can look at the projection first of all in the xy plane. You can see that the projection in the xy plane is the it's a semicircle of radius 1. Okay, so that alone tells me that this is the base, the projection in the xy plane, and that alone tells me that if I'm somewhere here, the angle, you see, cannot go beyond pi, and the radius cannot go beyond 1. So that tells me that it's going to be, the angle is going to be between 0 and pi. And that comes about because we're to the right of the xz plane. And because we're inside that cylinder, the radius has to be at most 1. Okay? And it's the z value that's a little bit more complicated because the z value has to be between 1 minus x squared minus y squared and z equals 4. And we almost won in the transformation to cylindrical coordinates, except that there is still some x and y lingering there. So we want to do the complete transformation by changing x squared plus y squared to r squared. So this is 1 minus r squared is less or equal to z is less or equal to 4. And now there's no x and y's in the description of z. There's no x and y's anywhere. So now we've won. That's the region in in cylindrical coordinates. So now I can integrate. The integral will be the integral from 0 to pi, from 0 to 1 in radius, and from 1 minus r squared to 4 in z value of what function? What function am I integrating? The function 1, but I don't have anything to do with the function. I don't have to transform it in any way. But I do have to multiply by the conversion factor that I've transformed this into some cylindrical coordinates. So there's an r, dz, dr, d theta. And let me just do the very first step of that would be the integral from 0 to pi, integral from 0 to 1. It's rz between 4 and 1 minus 4 squared. So it's r times 4 minus 1 minus r squared, dr d theta. And that becomes this integral from 0 to pi, integral from 0 to 1 of 3r plus r cubed dr d theta. And if you complete this integral, you get 7/4 of pi.